Have you ever just stopped to think about the device you're watching this on? I mean, it holds more computing power than all of NASA had back in 1969. But its direct ancestor? That was a machine that weighed 5 tons, filled an entire room, and couldn't do much more than basic math. So how in the world did we go from that behemoth to what's in your pocket? Well, that's the incredible story we're going to unpack.
You might look at that and think, nothing. But the answer is they share a direct line of descent, a common ancestry. The journey from this massive, single-purpose machine to the indispensable tools we carry with us every day, it's one of the greatest stories of human ingenuity, and we are going to trace every single major leap.
And this table just lays it all out, doesn't it? It really puts the scale of that progress into perspective. You've got the Mark I from 1944, 5 tons of steel and wiring dedicated only to calculations. And on the other side, a device that weighs a few pounds and can do, well, pretty much everything. Connect you to the world, create art, run a business. The journey between those two columns is exactly what we're exploring.
So, here's our roadmap. We're going to start with the history, breaking it down into 4 distinct generations of progress. Then, we'll take a look at all the different types of computers that exist today, explore 2 fundamentally different ways they think, and finally, we'll peek into the future, at the mysterious and still undefined 5th generation.
All right, let's dive into that central question. How did technology shrink so dramatically while getting exponentially more powerful? The answer isn't just one single invention. It's a series of revolutionary breakthroughs that defined these distinct eras, or as we call them, generations of computing. And thinking about this evolution in terms of generations is really the best way to see the pattern. See, each new generation was sparked by one core technology that solved the biggest problems of the last one. It unleashed a whole new wave of innovation and made what was once impossible, possible. Our timeline kicks off in the 1940s, right in the age of these giant, glowing vacuum tubes. Then, the transistor shows up and completely changes the game. After that, the integrated circuit figures out how to cram thousands of those transistors onto one tiny chip. And finally, the microprocessor puts an entire computer brain onto that chip, kicking off the personal computer revolution that we're all still living in today. So the heart of every single first-generation computer was this thing, the vacuum tube. You can kind of think of it like a small glass light bulb that could act as a switch, turning a signal on or off. It was the fundamental building block that made all of this possible. But, and this is a big but, it came with some absolutely massive drawbacks. And those drawbacks really defined these early machines. I mean, because they needed thousands of these tubes, they were enormous, they used these clunky magnetic drums for memory, and generated so much heat they needed dedicated industrial-strength cooling units just to keep from melting down. They were true giants, in every sense of the word. And then, in 1947, over at Bell Labs, the solution was born, the transistor. This tiny little device could do everything a vacuum tube could, but it was exponentially smaller, used a tiny fraction of the power, and was way, way more reliable. This wasn't just an improvement, it was a complete game changer. And the impact of the transistor was immediate. All of a sudden, second-generation computers were way smaller, faster, and they ran cool. This meant they weren't just stuck in specialized labs anymore, they could be installed in businesses and universities, becoming much more practical tools, even if they did still rely on really complex programming. So naturally, the next question for engineers was, okay, how do we pack even more of these transistors into a smaller space? And the answer was the integrated circuit, or IC. The genius move here was figuring out how to etch not just one, but thousands of microscopic transistors onto a single, tiny chip of silicon. Now, this didn't just make computers more powerful, it made them exponentially cheaper and more accessible. And this is the era where we see a huge shift in how we humans relate to computers. We start moving away from things like punch cards and printouts, and we see the introduction of keyboards and monitors, the first time an ordinary person could actually interact with a computer in real time. And that innovation leads us straight into the 4th, and you could argue the most impactful generation. The breakthrough here was the microprocessor. This wasn't just about putting more transistors on a chip. This was about putting the entire central processing unit, the actual brain of the computer, onto one single piece of silicon. And that one invention, it changed everything. In 1971, the Intel 4004 became the first microprocessor sold on the market. Pretty soon, hobbyists could build their own PCs from kits. By the early 80s, machines from Apple and IBM were showing up in homes and offices. And by the 90s, connecting all these personal computers together gave us the internet, which just fundamentally reshaped society. So, that wild journey brings us to today, where the word computer doesn't just mean one thing anymore. We're now living in an ecosystem with a whole family of different machines, each one designed for a different scale and a different purpose.
At the very, very top of this family tree, you have the supercomputer. And its secret weapon is something called parallel processing. Instead of doing one task at a time, just really, really fast, it breaks a massive problem into thousands of smaller pieces and has an army of processors work on all those pieces at the same time.
This chart gives you a sense of the mind-boggling scale we're talking about. If a personal computer's power is our baseline, a mainframe is a huge step up. But a supercomputer? It's in a totally different dimension. These things are built for tasks like accurately forecasting a hurricane's path or simulating the origins of the universe, problems that are just way too complex for any other machine. So what about mainframes? Well, they're kind of the unsung heroes of the global economy. As our source material puts it, they are built to process enormous amounts of data with rock-solid reliability. Think about it. Every time you use an ATM, book a flight, or make a purchase online, there's a really good chance a mainframe is working in the background, making sure that that transaction happens flawlessly. And then, of course, we have the branch of the family we all know and love, the personal computer. And even this category is incredibly diverse, right? It's everything from the powerful desktop rig in a gamer's room, to the laptop you work on, to the tablet you might even be watching this on right now. Okay, so beyond just their size and power, there's a much more fundamental difference in how computers can be designed. It really all comes down to two very distinct ways of processing information about the world.
You're using a computer right now, this very second. But have you ever really stopped to think about how it works? Well, today, we're going to peel back the case on this amazing device you use every single day and demystify the magic that's happening inside that box.
I mean, really think about it. You click, you type, you watch videos, you create stuff. But how does a simple collection of plastic, metal, and silicon actually do all of that? Well, it all comes down to this incredible partnership between two totally different but completely inseparable ideas.
Okay, so here's the best way to think about it. A computer is kind of like a person. It has a physical body, that's the hardware, and it has a mind that gives it purpose and tells it what to do. That's the software. The body has all the potential in the world, right? The muscles, the bones, but without the mind giving it instructions, it's just a lump of parts.
So, hardware is basically anything you can physically kick if it's not working. Just kidding, mostly. It's the monitor you're looking at, the mouse in your hand, and yep, all those complicated little circuits and chips tucked away inside the computer's case. It's the tangible stuff.
Software, on the other hand, well, that's the ghost in the machine. You can't touch it. It has no physical form. It's just a massive collection of instructions, the code, the programs, like your web browser or your favorite game, that tells all that physical hardware how to function. It's the intelligence that actually brings the body to life.
All right, so let's start our tour with the body. We'll kick things off with the parts we all know and see every day before we dive into the really cool stuff hiding inside.
On the outside, you've got the stuff you know well. The case. That's its protective shell. The monitor, that's your window into the whole digital world. The keyboard and mouse, that's how you talk to it. And all the extra stuff you plug in, printers, speakers, you name it. Those are called peripherals. You can think of these as the computer's senses and its tools for interacting with our world.
But let's be honest, the real action isn't on the outside. To really get how a computer works, we have to pop open that case and take a look at the vital organs that make everything happen.
The very first thing you're going to see is this huge, sprawling circuit board. This is the motherboard, and you can think of it as the central nervous system of the computer. Literally every single component plugs into this thing. It's the foundation that allows every part to talk to every other part.
And sitting right there on the motherboard is the most important chip of all, the CPU, the central processing unit. Now, if the motherboard is the nervous system, the CPU is, without a doubt, the brain. Every single command you give, every tiny calculation that's needed, it all funnels right through the CPU. This is the engine that does all the heavy lifting, all the actual thinking.
Now, for any of this to work, a computer needs memory. But here's the thing, it's a constant balancing act between speed and, well, permanence. And that's why it has two kinds.
First, you've got RAM, which is like your computer's workbench. It's super fast memory that holds all the data for the programs you are actively using right now. But just like a workbench, the second you turn the power off, it gets wiped completely clean. That's where the hard drive comes in. The hard drive is the filing cabinet. It's slower, sure, but it's your permanent, long-term storage. It's where your files, your photos, and all your software live, kept safe and sound even when the power's off. So, we put together the body, all the hardware. But right now, it's still just a very powerful collection of parts, sitting there waiting for a command. To bring it to life, we need to introduce the mind, the software that's going to make it all work together.
So, how do we bridge that gap? I mean, how do you, the user, tell that fancy CPU what to calculate, or tell the hard drive which file you want to open? You need a translator. You need a manager, a master controller.
And that controller, that's the operating system, or the OS. You know it by names like Windows, or Mac OS, or Android. The OS is the very first program that starts up, and its entire job is to manage everything. It's the crucial middleman that lets your apps, like a web browser, actually communicate with your physical hardware, like your Wi-Fi card.
Think of the OS as the ultimate conductor of a giant orchestra. It's constantly juggling all your applications, making sure each one gets a slice of the CPU's attention. It manages that workbench, the RAM, so your programs don't step on each other's toes. And it directs all the traffic to your hardware, so when you click print, it knows exactly how to talk to the printer. It is the foundational system software that allows all of your other application software, the games, the browsers, the word processors, to even run in the first place.
But, talking to an operating system hasn't always been as simple as just clicking an icon. The way we interact with this mind has gone through a massive, massive evolution.
You see this? In the early days, this is what using a computer looked like. A black screen, a blinking cursor. If you wanted to run a game, you had to know the exact cryptic command to type in. There were no icons, no mouse pointers. It was powerful for sure, but unbelievably difficult for anyone who wasn't a total geek.
And this timeline just shows you the incredible journey. We started back in the 80s with DOS, that world of the blinking cursor and secret commands. Then came the revolution, Windows 95. It gave us the graphical interface we all know and love today, icons, folders, and that famous start button. That interface just got better and better over the years, more stable and powerful with versions like Windows 7. And today, operating systems are built to adapt, working seamlessly whether you're using a mouse, a keyboard, or a touchscreen.
This shift to a graphical user interface, or GUI, it was everything. It was a complete game changer. It replaced these abstract, hard-to-remember commands with intuitive, visual things we could understand. Files became little documents inside folders, and programs became clickable icons. It was this single innovation that took the computer from a niche tool for hobbyists and experts to a device for absolutely everyone.
So, after our tour of the body and the mind, let's bring it all back together, one last time, and really lock in on the fundamental relationship at the heart of every computer.
When it's all said and done, it comes down to this simple, powerful partnership. Hardware is the stage, but software is the play. You can have the fastest, most powerful processor in the world, but without an operating system and applications, it's just a very expensive and very silent piece of silicon. They are two halves of a whole, and one is completely, totally useless without the other. Which, of course, leaves us with a really fascinating question. We're watching hardware shrink down to microscopic sizes, while at the same time, software, powered by things like AI, is becoming almost infinitely intelligent. So what new magic will this timeless partnership of body and mind be able to create next? What's the computer of tomorrow going to look like? That's the question we'll leave you with. Thanks for watching.